Now for section 2.7, the Cantor set and the Cantor-Lebesgue function. So what we're doing here is looking a little bit more at some properties of measurable sets. One thing that kind of remains unresolved is how cardinality and measure exactly interact. We know that countable sets have measure 0, and I've commented a bunch of times that the converse doesn't hold. There exists a non-countable set, an uncountable set, which has measure 0 as well. And the standard example of that is the Cantor set. So in this section, we'll define the Cantor set. It'll give us an example of an uncountable set of measure 0. Maybe topologists are quite interested in the Cantor set for various reasons. Our reasons are measure theoretically based, and that's in my opinion, that's the big punchline. Now I've got a supplement to this section prepared where we'll go through and look at some cardinalities of collections of sets. We'll look at the cardinality of the sigma algebra of Lebesgue measurable sets, and we'll look at the cardinality of the collection of non-measurable sets. So I'll save that for a supplement, though that's deeply based on the Cantor set also. In this section, 2.7, we'll use the Cantor-Lebesgue function to show there are measurable sets which are not Borel, and we can make a cardinality argument about that as well, borrowing some results from elsewhere, and that's done in the supplement also. Okay, so here comes the definition of the Cantor set. Actually, let me draw pictures and make this a little bit lengthy. It's an iterative process, which means a little hard to grasp from what's given here. From a picture, it's pretty clear what's going on though. So we're going to start with the interval, I equals 0 to 1, closed interval. We're going to iteratively remove open middle thirds of the interval and resulting subintervals. So we'll take the interval 0, 1 and remove the interval in the middle, 1/3 to 2/3. Then we're going to remove the interval from 1/9 to 2/9 and the interval from 7/9 to 8/9. Then we're removing 4 intervals, and then we're removing 8 intervals. So you see a doubling in the number of intervals we're talking about here. As I say removed, we're ultimately going to do a complement of the union of these intervals. So here's what's going on. Graphically, we're starting with the interval from 0 to 1 and removing this part, leaving you with 2 little closed and bounded intervals, interval from 0 to 1/3 and the interval from 2/3 to 1, not to scale. I've intentionally made this image not to scale so you can see better what's going on. Then we're going to do the same thing to each of these 2 subintervals. So we'll take this interval, remove the middle third. This interval is 1/3 in length, so thirds are 1/9 in length. So we have the interval 0 to 1/9. We're throwing out 1/9 to 2/9, and we're keeping 2/9 to 3/9, or third. And do the same type thing over here. Leaving us now with, if you imagine the open intervals in color being removed, leaving us with 1, 2, 3, 4 little closed subintervals. Split each of those up by removing middle thirds. So do it again. This time you're removing little subintervals of length 1/27. This time we had, 4 intervals up there in black. So we'll have 4 of these intervals of width 1/27 that are being removed. Notice how many little connected black subintervals you have now after you remove the open intervals in color. There should be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Next, we'll remove the middle thirds of those 8 black subintervals, closed and bounded, by removing, let's see, 1/81, little subintervals of length 1/81, and so forth. So at every stage, we're removing middle thirds of what you have from the previous stage. So in that sense, this is an iterated process. Here specifically is what we had in the picture, O1, O2, O3. These were the red interval, I think it was a blue interval, and then green interval removed, and the pattern continues. So these are the open sets that we'll remove, take their complements with respect to the interval 0, 1. So from the interval 0, 1, first we'll remove that middle third, leaving these two intervals. Then we'll remove the middle thirds of each of these, leaving us with these 4 subintervals. That's what we have down here. We're denoting these C sub 1, C sub 2, and so forth. That's what we have down here. Next, remove middle thirds of each of these, producing 8 subintervals, and that's the little black subintervals given here, and so forth. So it's the open things that are being removed. At each stage, you're left with a collection of closed and bounded intervals. At step K, there are 2 to the K closed intervals of a total length of 2 to the K over 3 to the K. So we've gone through, and when K equals 1, we've got here 2 to the K intervals. Each is of length 1/3. There's 2 of them for a total length of 2/3. So we get this 2 to the K, 3 to the K for these collections of closed intervals here. Now we're going to define the Cantor set to be the intersection of all these C sub Ks. There's the math of it. More geometrically, that's why I keep describing it in terms of removing middle thirds. We pulled out the middle third in this first step. That's gone. Now we'll pull out these middle thirds. The stuff in black is left. Now we'll pull out middle thirds from each of those constituent sets. The stuff in black is left, and so forth. So to each of these little black subintervals, we're removing middle thirds and repeating that process. So it's the points in black throughout that we're interested in. Those are the points that make up the Cantor set. The other stuff is the stuff that's been thrown away. Any observations? Every time we were throwing away open intervals, in fact, we're throwing away disjoint open intervals every time, the colored open intervals here. We removed a countable number of them. A countable disjoint collection of open intervals makes up an open set. In fact, you don't need countable or disjoint. An arbitrary union of open sets is open, but the thing we're removing is an open set. We're removing it from the closed interval 0, 1. Pretty immediately, we have the fact that the Cantor set, though an exotic set, it's just a closed set. So topologically, it's not exotic at all. We'll state this in more detail down below. We have that the Cantor set is the interval 0, 1. Set minus the union of those O sub Ks as we defined it, the things that have been taken away. So we can write the interval I as a union of the Cantor set along with the things that were removed. And we get disjoint unions all over the place. We get a disjoint union here because we've removed it. The Cantor set is what we get by removing all this other stuff. So there's disjointness there. And of course, you see from the picture, if you like, the little O sub Ks, all these little colored open sets are disjoint by construction. Proposition 2.19 says the Cantor set C is closed, uncountable, and of measure 0. Closed, no big surprise on that. Uncountable, let's look into that. Okay. So there's the claim. First, about closed, the Cantor set is the intersection of those C sub Ks. This was the part left, the part in black at each stage, and we removed more and more. So what you do is intersect all the C sub Ks to get the Cantor set. De Morgan maybe is somewhere in there. Each of the C sub Ks were closed. They were finite unions of closed and bounded disjoint intervals. So closed, no problem there. So the Cantor set itself is closed. If it's closed, then it's measurable. Closed sets are measurable. So topologically, Cantor set's not that exotic, but it has some other shocking measure theoretic properties. Each of the C sub Ks, we might jump back to the picture if needed. is the disjoint union of 2 to the k intervals, each of length 1/3 to the k. We commented on that. We said something about the total length was this 2/3 to the k. We've got countable additivity. Everything we're dealing with here is measurable. The open intervals are measurable. Their complements are measurable. Their complements are those closed sets. So the measure of each c sub k is 2/3 to the k. Let's take a peek at the picture again of the Cantor set. This is a good picture. Okay. I'm looking at the black parts. 2 times 1/3. Looking at the black parts. 4 times 1/9. 4 is 2 squared and 9 is 3 squared. So you see the pattern here. We get 8. 2 cubed, each of length 1/27, 1/3 cubed. So that's what's going on in terms of the measures of the c sub k's. Now we've got the Cantor set defined to be the intersection of those c sub k's. So we can say that by monotonicity, the measure of the Cantor set is less than or equal to the measure of c sub k for all k. It's defined to be an intersection of all these. So C is a subset of all of the C sub k's. Monotonicity then will tell you the measure of C sub k is less than or equal to the measure, the measure of the Cantor set is less than or equal to the measure of the C sub k's. This holding for all k. And we saw by definition the measure of the C sub k's is 2/3 to the k. Holds for all k, a natural number. K gets large, 2/3 gets small. 2/3 to the k gets small, approaches 0. So that must be that the measure of the Cantor set is 0. Okay, so there's most of what we wanted. Closed set, measure 0, the cardinality stuff we need to deal with. And we do so as follows. The supplement has a slightly different argument based on some base 3 representations of numbers. Assume the Cantor set is countable. Say it consists of lowercase c sub k's, k equals 1 to infinity. So this gives an enumeration of the elements of the Cantor set, if there is such a thing. So assume so. We're going for a contradiction. Now C1 consists of 2 disjoint closed intervals. So one of them fails to contain c sub 1, denoted f sub 1. Let's do this one more time, then we'll look at the picture again. In c sub 2, there are 2 disjoint closed intervals, which are subsets of f sub 1. One of these fails to contain the point c sub 2, denoted as f sub 2, and so forth. Okay, so we've pretended there's an enumeration of the entries of the Cantor set. The Cantor set is contained in these black subintervals. What we said is, if there's an enumeration of the Cantor set, then pick that first element of the Cantor set, lowercase c sub 1. It's got to lie in either here or here, first off. Now, granted, you're going to remove a lot more stuff, but if it's in the Cantor set, it's got to be in one of these 2 intervals. Say it's this one. All right, now let's move down, concentrating on what we started with here. Let's move down and look at these 2 things. C sub 2 has to be in one of the black intervals given here. It can be in only one of them because they're disjoint, so it's not in one of these. I mean, for all I know, it may not be in both of them. But it's not in one of these. Say it's this one. Now we'll go down, taking this subinterval, subdivided, and say C sub 3 is not in one of these. Pick that, and that becomes f sub 3. So we're creating this sequence of closed intervals. As I just described it, this would be f1. I think I chose this for f2. Say maybe this one is f3, and it may bounce around a little bit. But we do have this nestedness on this collection of closed intervals we're creating. And those closed intervals get shorter and shorter in length. Back to the proof. So that's how the f sub k's are being chosen A little summary. The F sub k's are closed. They're those little closed subintervals chosen stepwise from the creation of the Cantor set. F sub k plus 1 is a subset of F sub k. We chose them to be nested. F sub k is a subset of C sub k. Okay, yeah, we had C sub k being the collection of all the little black subintervals at each level. So yeah, we chose F sub k to be one of those. So yes, we get that subset inclusion, and we chose the C sub k, chose the F sub k such that a given C sub k was not in F sub k. All right, now this first property says we've got a collection of closed sets that are nested like this. It's a decreasing sequence of sets. We had used that terminology when looking at continuity of measure. So it's that idea. It's decreasing sequence of sets. By the way, they're closed sets. The nested set theorem, not given a number in the book, but it's expressed on page 19, says when you have a nested collection of closed sets, their intersection is non-empty. A nested sequence of closed sets, then their intersection is non-empty. Sets of real numbers. So there must be something in the intersection of all of these by the nested set theorem. Probably explored this somewhere in senior level analysis, probably senior analysis 1. So let X be the thing that's in the intersection of those F sub k's, because there's something there. That intersection is non-empty. Property of the real numbers. It's based on completeness of the real numbers. Property 2 says F sub k is a subset of C sub k. Okay, well then the intersection of all the F sub k's is a subset of the intersection of all the C sub k's. By the way, the intersection of the C sub k's was the Cantor set by definition. So this point X that we found is an element of the Cantor set. Problem is, it can't be in any of the F sub k's, it turns out. Okay. Or it can't be in the intersection of the F sub k's. But we had the Cantor set represented as C sub 1, C sub 2, and so forth. So this X has to equal one of those subscripted C's. X has to be C sub n for some index n. But then this C sub n, this X value, it can't be, should read in the element of, if we'd have to have that an element of the intersection of all of these, but the intersection of all these is a subset of F sub n. It's a subset of all of these F's. In fact, it's an intersection. So F sub n contains the intersection of all of these. We've got that X is an element of all of these. Should read element of, not equals, typo there. But we created this such that C sub n is not in F sub n. That's how we made these F's. And there's the contradiction. So the assumption that C is countable is false, and so C must be uncountable. Again, there's an argument in the supplement to this section based on binary and ternary representations of the numbers from 0 to 1. It also gives an argument that the Cantor set is uncountable. Nothing wrong with this version here. This is a new section, I think, to the Royden and Fitzpatrick book. They mention the Cantor set in passing at best in previous editions of the book. And this argument based on binary and ternary representations, I've seen that more often than I've seen this argument here. Nothing wrong with this. This establishes a non-countability. And what we're left with then is, the punchline is, we just established the existence of an uncountable set of measure 0. So how does cardinality relate to measure? Not well. Countable sets have measure 0, full stop. The converse doesn't hold because there's uncountable sets of measure 0. The contrapositive holds. If a set has positive measure, then it must be uncountable. That's just logically equivalent to the statement that countable sets have measure 0, though. So we really don't get a relationship between cardinality and measure. And this seals the lid on the coffin that there might be such an involved relationship. There isn't. Look at measure zero sets. Could be countable, could be uncountable. Take the Cantor set, for example. This we're going to get lots of mileage out of in the supplement. Okay, they choose to introduce a Cantor function as Cantor-Lebesgue function, as they call it in the title of the section. So we'll look at that and get similar mileage out of the Cantor set. What we're going to argue in the supplement to this section is two things. This, which is good news, the cardinality of the sigma algebra of Lebesgue measurable sets is Aleph 2. Okay, the following assumes the continuum hypothesis and maybe the generalized continuum hypothesis that allows me to deal with these cardinal numbers, Aleph naught, Aleph 1, Aleph 2. We need to go up to Aleph 2 in our conversations in this class because we want to talk about the power set of the reals. The reals have cardinality Aleph 1. So the power set of the reals under the generalized continuum hypothesis has cardinality Aleph 2. So our conversation about sets of real numbers is based on a collection of sets of cardinality Aleph 2. So what's the cardinality of the sigma algebra of Lebesgue measurable sets? Well, couldn't be more than Aleph 2 because it's a subset of the power set of the reals. It could be less than that though. Well, it turns out it isn't. And we can use that previous proposition, the fact that the Cantor set is uncountable and has measure zero. We can use that to establish this condition here. Actually, what we can establish is there's Aleph 2 sets of real numbers of measure zero. And you know measure zero sets, outer measure zero sets are measurable. They satisfy the Carathédor splitting condition. So good news. The cardinality of the sigma algebra of Lebesgue measurable sets is Aleph 2. That's as big as the power set of the reals, same cardinality. Yeah, there's some bad news we'll see in the supplement as well. I might ask, well, how many non-measurable sets are there? Turns out there's Aleph 2 non-measurable sets as well. And the proof is based on, in the supplement, the Cantor set. Some of the exercises from this section describe the construction of a fat Cantor set. We've produced a Cantor set of measure zero. They show how to produce a Cantor set of measure 1 minus alpha, where alpha is between 0 and 1. So it's a modification, creating a Cantor set maybe by not removing middle thirds, but removing something else. And so when you go through and see how much has been removed, you see there's a part left. Right, we didn't remove everything in terms of length. We'd have the sum of the lengths of the things removed not equal to 1, like we do in what we did, but something else. And that's how you produce the 1 minus alpha measure fat Cantor sets. In exercise 240, it stated that an open set can have a boundary of positive measure. The open set is the complement of any fat Cantor set. The boundary is in the fat Cantor set itself. So I mean, think what's happening here. You think of open sets as a countable number of disjoint open intervals. So it seems its boundary would just be the endpoints of those intervals. That would be just a countable collection of points. But there's something wrong. There must be something wrong with that little leap I took from saying, well, I know what open sets look like, to the conclusion that, well, their boundaries must just be the endpoints. Maybe it's more involved than that. It must be more complicated than that. The boundary, it would seem, would just be the endpoints. It's got to be more complicated than that, or you couldn't have this weird boundary of an open set having positive measure. So there must be something more complicated than that to the boundary of open sets of real numbers. So I leave that to the exercises. Let's talk now more about the Cantor-Lebesgue function. First definition, this is a Calculus 1 definition and an Analysis 1 definition. A real valued function f that's defined on a set of real numbers is increasing if f of u is less than or equal to f of v whenever u is less than or equal to v. So calculus 1 type definition. Input bigger values, get bigger outputs, crudely put. Strictly increasing if I replace those with strict inequalities. So it strictly goes uphill, strictly increasing when you put in larger input values. We're going to look at increasing in the beginning. We'll do the strictly increasing here in a sec, but first we're going to define a function that will be increasing but not strictly increasing, and that's the Cantor-Lebesgue function. So two things. Here's the setup for the definition, and then we'll draw a picture. Actually, I'll look at a graph that I found somewhere online of what the Cantor-Lebesgue function looks like. Let k be a natural number. Define increasing function phi on the interval 0, 1, set minus c sub k, where c sub k was defined above, which consists of 2 to the k minus 1 disjoint open intervals to take on the values 1/2 or 1 over 2 to the k, 2 over 2 to the k, 3 over 2 to the k, and so forth, up to 2 to the k minus 1 over 2 to the k. Let's look at a picture. Here's some algebra that lays these things out, but here's what we're doing. Yeah, let's actually go back and look at the Cantor set. Okay, so we're defining this on the c sub k is the part that was removed. C sub k is this part that was removed, because we denoted the other parts as the c sub k's. Define the function to be 1/2 here. Now we're going to have these pieces, going to define it to be 1/4, 2/4, 3/4. 2/4 is a half. That's consistent with what we had before. Now we're going to define it in terms of eighths. 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8. Notice how it works. Oh, and also I said 6/8 here and 3/4 here. So we got consistency. We're not changing the definition when I go to the next level. So that's how the Cantor-Lebesgue function is defined in terms of these 1 over powers of 2 and the multiples of 1 over powers of 2. Okay. That, let me finish the definition. Here it is spelled out explicitly, not reducing. Right? It's easier to see the pattern. For example, when k equals 2, 1/4, 2/4, 3/4, right? We had expressed those a couple of different ways. The 1/3 to 2/3 is fatter than these other two. It's 3 times the size, if memory serves. K equals 3, we'd have 7 pieces, right? 1/8 through 7/8 is how we define those. We looked at the 6/8, it's the same as 3/4 from the previous level. In this way, phi is defined on those open intervals, the complement of the Cantor set. For x in the Cantor set, define phi of x to be 0 when x equals 0. So phi of 0 is 0. And define phi of x to be the sup of phi of t such that t is in the open set up here, the complement to the Cantor set, intersect the interval 0 to x. So I'm looking, it says here, we're defining phi of x. It says look to the left of x and see what, I don't know how the function is trending, and define its value at x, an element of the Cantor set, to be the sup of these values. All right, so that's how we're defining it on the interval 0, 1. Phi is the Cantor-Lebesgue function, and we get something like this. So we get it a constant of 1/2. Here's your link, a hyperlink on where I found this. Pictures of the Cantor-Lebesgue function, they won't be rare online. But notice it's 1/2 between, it's not calibrated with an idea of thirds or whatever. They've just done it at 2/10 increments. But here's 1/3 to 2/3. It takes on the value 1/2. Here's what we're getting in the 1/4, 3/4, those two pieces. There's a little piece related to the eighths. There's 1/8, 2/8, 3/8, 4/8 or 1/2, 5/8, 6/8 or 3/4, 7/8. And it's got this self-similarity. And if I look between, I see these little steps here. And between that, the resolution starts to kind of vanish. But there's a repeated pattern of this. There's a fractal nature to it. If I were to take this little piece here and magnify it, it'd look like the whole thing. So it has this self-similarity type behavior. And the claim is the Cantor-Lebesgue function phi is an increasing continuous function that maps 0, 1 into 0, 1. Its derivative exists on the open interval O, doesn't exist on the Cantor set, and the derivative is 0 on that open interval. Alternative statement there is the derivative is 0 almost everywhere on the interval 0, 1. The only place the derivative isn't 0 is on the Cantor set, that is measure 0. All right, so keep in mind this picture. Let's go through this argument about increasing, continuous, and mapping 0, 1 to 0, 1. Next, okay, there's the claim for the increasing. Okay, we're going to do this case-wise. I need to look at U and V, and it depends where they come from as to how phi of U and phi of V is defined. Phi's increasing on the set O. Right, we built it to be increasing on the set O. We had that collection of steps. So if U and V are both in O, the little open intervals that were removed to create the Cantor set, and U is less than or equal to V, then phi of U is less than or equal to phi of V. You don't get the strictly increasing. Remember the picture. We created it to be constant, kind of like a step function, a really involved step function, but we made it constant on those little intervals that were removed. So certainly not strictly increasing, but increasing on set O. All right, but that's not everything between 0 and 1. We got to deal now with U less than or equal to V, say where U is in the open set and V is in the Cantor set, except for 0. 0 we'll deal with right at the end. Well, we had defined phi of V. We had defined phi of V for such elements, Cantor set, except for 0, to be the sup of phi of T, where T is an element of O, intersect the interval from 0 to V. We extended the function phi from set O to the Cantor set using this definition. So notice all these phi of T's, the T's are elements of O, T values that are less than V. All right, well now, if we're defining phi of V to be the sup of a bunch of phi of T values, these T values are in O, and we've got U less than or equal to V. One of these T values is between U and V. We must have a strict inequality here because U is in O and V is in the Cantor set, so there's a little room between them. And there's a T in there. All right, well, for those T values, which are greater than U, we're getting phi values greater than U because we're comparing phi at an element of the set O to phi at an element of set O, where U is less than T. That's the one thing we established above. So indeed, the sup will be greater than the phi of U under these conditions. And that gives us increasing. Phi of U is less than or equal to phi of V when we have U in O and V in the Cantor set, except for 0. Next. All right, suppose U is less than V, and this time the lesser one is in the Cantor set, except for 0, and V is in O. And the last case will be U and V are both in the Cantor set, except for 0. This time, phi of U is defined in terms of a sup. Now we're taking phi values for T and O, and T is less than U. Over here, phi of V, V is also in O, so if I compare the phi of T's and the phi of V's, both of which involve T in O and V in O, and I know how the function behaves on set O, I get the inequality. Follows from right there, except we've got T's in this little set here. All of these phi values are less than or equal to phi of v, so the sup is less than or equal to phi of v, and the sup is by definition the phi of u. So it's quite similar to the argument up here. So we've got phi is increasing for these values as well. That leaves u and v both in the Cantor set. Let's make them distinct. If they ain't distinct, then we get the less than or equal to. We get it equals to. Suppose we take u and v to be distinct elements of the Cantor set and not zero. Then there's some w and o, the open set, between u and v. I take two elements of the Cantor set. At some point, you remove points between them. And when you remove them with some tiny little subinterval that now makes up set O. Let W be in that little subinterval that was pulled out between U and V. So now we've got an element of the Cantor set as compared to that O, and I know that produces an inequality of this sort. And we've got an element of set O compared to an element of the Cantor set, and I know that produces this type of inequality. That was the last two arguments we had. So I can paste those two arguments together to show that we get, again, phi of u is less than or equal to phi of b. And that takes care of everything except maybe phi of 0, and phi of 0 was 0. And all these things are producing non-negative numbers. So we're good dragging 0 into the conversation as well. So that takes care of the increasing claim. Next, we need the continuity claim, the mapping claim, and the derivative claim. See, the derivative claim will be easy because we got the function to be a constant on set O. Well, on the components of set O. Continuity. Okay, so this will be an epsilon delta type thing. First, phi is continuous at each point of O. It's constant on the little open interval components of O. One more time. When I talk of O, I'm talking of the parts that were removed. Yeah, so it's constant on the open components of set capital O. So that's a continuous function. Continuous functions, constant functions are continuous. Okay, so we got the continuity on O. Now consider x sub 0 to be in the Cantor set. Let's stay away from the endpoints. I have to take care of the endpoints separately. For k, a natural number sufficiently large, we have that x sub 0 lies between two consecutive open intervals in the complement with respect to 0, 1 of that c sub k. Let's look at the picture of the Cantor set again. So we've chosen an arbitrary element of the Cantor set. Back up here. All right, suppose we chose a number right in here. Up here, there weren't two consecutive sets that lies between. Down here, there is. And down here there is as well, but it's a different set. So choose some element in the Cantor set. There occurs a first time, in fact, c sub k, where this lies between here and here. And these maybe are kind of far apart. I can get them closer together if you like. We're going for continuity with epsilon delta definitions. So for k sufficiently large, we have that x sub 0 lies between two consecutive open intervals in 0, 1 minus c sub k. Let a sub k lie in the lower of those two components and b sub k lie in the upper of those two components. Function phi is defined to increase by 1 over 2 to the k jumps across consecutive intervals in 0, 1 set minus c sub k. So we've chosen x sub 0 to be sandwiched between a sub k and b sub k as we've denoted it. And we know a sub k and b sub k occur in consecutive components. Where's the word consecutive components, consecutive open intervals. So the difference in the phi values at those 2 points is 1 over 2 to the k. We set it up to have those 1 over 2 to the k little jumps from one open interval to the next. We can make K arbitrarily large, so we'll still have such consecutive intervals existing as observed in the picture a second ago. So if we take epsilon greater than 0 and let K be chosen such that epsilon is less than 1 over 2 to the K, so we get those function values within 1 over 2 to the K, sorry, within epsilon of each other. But given epsilon, we can choose such a natural number K. For delta, such that delta is less than the minimum of x sub 0 minus a sub k and b sub k minus 0. So measuring the distance from x sub 0 to that a sub k and b sub k, right? This distance and this distance, taking delta to be the minimum of those two. A sub k and b sub k are described in elements as mentioned in the complement of c sub k. Then we've got x sub 0 minus x less than delta, implying phi of x sub 0 minus phi of x is less than phi of b minus phi of b sub k minus phi of a sub k. We're using the increasingness here. I think what happens, we've got phi of b sub k, that's going to be greater than phi of x sub 0 because we've got this relationship here. And we're going to have phi of x, it lying between these two, phi of x to be greater than phi of a. So I get that right. I got an absolute value in there to further muddle things up. We've used the increasingness to draw the conclusion that this absolute value is less than or equal to the difference of the functions. And we know the functions are within 1 over 2 to the k of each other, and that's k was chosen such that that's less than epsilon, which the punchline here is this part. X sub 0 minus x less than delta implies phi of x sub 0 minus phi of x in absolute value less than epsilon. So that is the very definition, the epsilon delta definition of continuity at point x sub 0. So phi is continuous at point x sub 0. That shows continuity on the Cantor set. So first, continuity on set O. Second, continuity on the Cantor set, no, except for 0 and 1. Finally, something a touch more informal. Phi takes on the value 1 over 2 to the k when x is in the Cantor set and close to 0. Let's look at the picture and a similar behavior at the other end. Let's look at the picture of the function. So remember, as we cut this up into these smaller pieces out, we're getting 1 over 2 to the k's out over here close to 0. So we're getting function values out there close to 0 over here. At the 1, we're getting, 2 to the k minus 1 over 2 to the k, 1 minus 1 over 2 to the k out here, which is close to 1. So if I may be a touch informal, when I input values close to 1, we output values close to 1. When we input values close to 0, we output values close to 0. And it comes straight from the definition of the function. So we've got continuity at 0 and 1 as well. So we got continuity on the interval 0 to 1. So we've established increasing and continuous on its domain, 0, 1. The derivative. Phi is constant on the open intervals in O, the little flat steps. So the derivative is 0 for all x in O. C has measure 0. We argued that above, proposition 2.19, I guess it was. The measure of O is, excision property holds here. We're dealing with measurable sets, so there's no weirdness going on in this. The measure of 0, 1, set minus C, that's what O is. We can take the difference of the measures as long as this is finite, it's 0. And so we get the measure of the interval 0, 1, which is 1. So we've got that the derivative exists and is 0 on set O as claimed. The only thing we haven't dealt with is about the interval 0, 1, and actually we're showing onto. It maps 0, 1, little boo-boo there, maps it onto 0, 1. And this is true, but we want to show onto. Hey, phi of 0 is 0, phi of 1 is 1. We got an increasing continuous function. It takes that interval 0, 1, and it maps it onto the interval determined by the outputs, 0 and 1. Intermediate value theorem will tell you you get out every value between 0 and 1. So indeed, phi maps the interval 0, 1 onto, should be onto the interval 0, 1, as claimed. All right, let's back to the notes. Next claim, as we just got 2 more theorems to state, and then a little wrap up. Okay, next statement is, let phi be the Cantor-Lebesgue function and define a new function psi on the interval 0, 1 by psi of x equals phi of x plus x. So we've taken the Cantor-Lebesgue function and added x to it. The claim is psi is a strictly increasing continuous function that maps 0, 1 onto 0, 2. Okay, the continuity part is easy. That's continuous, and the identity function is continuous. Strictly increasing, phi was increasing, and the x function is strictly increasing. So that's pretty straightforward as well. We already knew we mapped 0, 1 onto the interval 0, 1 by the phi function. The adding x just stretches things a bit more to give us the interval 0 to 2 out. So not surprising in that behavior, but we'll go through the proof. Maps a Cantor set C onto a measurable set of positive measure. Okay, that's messed up. And maps a measurable set, a subset of the Cantor set, onto a non-measurable set. So we're taking a set of measure 0 and continuously mapping it to a set of positive measure. All right. Maybe that's not so messed up. We got a strictly increasing function. It might be stretching things as far as we know. It must be. It's mapping the interval 0, 1 to 0, 2. So I take it back. Maybe that's not so messed up. It's mapping, though, a measurable set to a non-measurable set. And we're going to use this to go through and draw some conclusions about some other non-measurable sets. So here's that idea again, popping up in this. So let's go through and prove this. Not that it's so much this we're interested in as the next result that tells us about something about Borel sets and non-measurable sets. Okay, so we're defining the psi function as phi of x plus x and making some claims. Psi is a sum of 2 continuous increasing functions, one of which is strictly increasing. The functions phi of x, which is continuous and increasing, but maybe not strictly increasing, and the function x, which is continuous and strictly increasing. So the sum is continuous and strictly increasing. We know psi of 0 equals 0. Psi of 1 would be phi of 1 plus 1. Phi of 1 is 1. So we get 2 out when we plug 1 into the psi function. The fact that we've got continuity and strictly increasing then tells you we've mapped the interval 0, 1 to the interval 0, 2. And we've done it using the Cantor function. That mapping, no big deal. But we've used the Cantor function in creating this. Okay, the interval 0, 1 can be written as a Cantor set, disjoint union, that open set O, and that's how we define the Cantor set as the complement of that open set O with respect to the interval 0, 1. Now the psi function is 1 to 1. So the interval 0, 2 can be by mapping this disjoint set with a 1 to 1 set. Why is it 1 to 1? Strictly increasing functions are 1 to 1. So the psi function is 1 to 1. So the disjointness is preserved by that mapping because of the 1 to 1-ness. Strictly increasing continuous function defined on an interval has a continuous inverse. Ring a bell. A result really from senior level analysis. Strictly increasing continuous functions defined on an interval has a continuous inverse. Well, if it's strictly increasing, it's 1 to 1 and it has an inverse. The fact that the inverse is continuous maybe isn't immediately obvious, but here's a link in the supplemental files to that result from my senior level analysis notes. Let's take that as given. Well, hey, this function psi is an increasing continuous function defined on an interval. Then this function psi has an inverse. Psi of C is closed and psi of O is open. Okay, I've got to appeal to the inverse images. Remember, inverse images of open sets under continuous functions are open, and the same holds for closed sets. It's proposition 1.22. I don't know if we went through that in our supplemental review, probably not. I don't rely on senior level analysis for that. But inverse images of open sets are open under continuous functions, and inverse images of closed sets are closed under continuous functions in the appropriate setting, and we're in the appropriate setting. So it must be that psi of C is closed. After all, its inverse image is C, and C is closed. And psi of O must be open. Its inverse image is O under psi, and O is open. So a subtlety on the fact we're using the continuity of psi inverse in this conversation, but a conclusion that this set is closed, that set is open. Closed and open sets are both measurable, so we've got these two things to be measurable. Cantor set's measurable, and the set O is measurable. All right, we already knew the Cantor set was measurable. We knew it was, I guess that's not what we're claiming. We're claiming psi of the Cantor set is measurable, and psi of the open interval is measurable. So there is a little something more to it. Okay. Set O consists of a countable disjoint union of open intervals, because every open set consists of a countable disjoint union of open intervals. These I sub k's, I could explicitly tell you what they are because we built them, right? We pulled them out of the interval 0, 1 in the creation of the Cantor set. I don't need to know which is which in this argument. I just need to know set O is a countable disjoint union of these I sub k's. Let the I sub k's be the connected components of O. It's those intervals we were talking about earlier. Then phi is constant on each of those I sub k's. Yeah, we built the Cantor-Lebesgue function like that. So we're about to do a translation invariance thing here. Psi maps the interval I sub k onto a translated copy of itself. Okay. Psi is phi plus x. Phi of x plus x. Psi of x is phi of x plus x. That's how we defined the psi function. The plus x part, that's just the identity. So we've got the identity function, and to that we've added some constant. The constant phi of, whatever value phi takes on this I sub k. So when we look at phi of x plus x on interval I sub k, the phi of x part is always the constant value that the Cantor-Lebesgue theorem gives us on interval I sub k. So we've got a constant plus the identity. We're translating this interval I sub k by the amount phi of x, where x is an element of I sub k. That's what you get when applying the psi function to the interval I sub k. All right. We're going to use this in translation invariance here at the bottom of the slide. Okay. Psi is 1 to 1. So if we look at the collection of sets, psi of I sub k, k ranges from 1 to infinity. The I sub k's are disjoint, so their images are disjoint. 1-to-1 function will preserve the disjointness. And we've got a bunch of measurable stuff. We've got countable additivity in particular. So when we take the measure of psi of O, that's the measure of psi of this disjoint union, because that's what O equals. The psi function applied to the disjoint union produces a disjoint union of the images. That's the 1-to-1ness up here that allows us to draw the set equality conclusion there. Now we've got a measure of a countable disjoint union. That's the sum of the measures, countable additivity there. We got the size in here. The psi of I sub k, that was just a translation of I sub k. If you like, I could say the measure of psi of I sub k is the same as the measure of I sub k and jump from here to here. Actually taking it through a conversation about lengths of intervals, if you like. I can jump from here to here. It's a translation invariance that gets us from here to here. Or we can say, well, psi of I sub k, that's an interval. So we get the length of that interval. Psi of I sub k is a translate of I sub k, so their lengths are the same. So I'm using translation invariance of length here. I could do it for measure here and skip a couple of steps. Anyhow, we get the sum of the measures of the I sub k's. Hey, those I sub k's are disjoint. That's equal to the measure of the union of the I sub k's. Equality, countable additivity, disjointness, and the union of the I sub k's is set O. We get the measure of O out. What do we accomplish here? We've shown that the measure of psi of O is the same as the measure of O itself. So the measure on that open set under this function psi, it didn't change. The measure of set O didn't change when applying this function psi to it. Are you surprised? No, it was really, it just took the pieces of that set O and translated them. And translation invariance is what made it work. So that part I'm not surprised on. All right. But what did psi do to the Cantor set? Measure of the Cantor set 0. Measure of set O is 1, established by excision principle, I guess. So the measure of psi of O must be 1 as well. After all, the measure of psi of O and the measure of O are the same. That must be 1. We've got the interval 0 to 2 written as psi of O, disjoint union, psi of the Cantor set. We made that claim on the previous slide. I know psi of O has measure 1, so psi of the Cantor set must have measure 1 as well. So this function psi has continuously mapped the Cantor set onto a set of positive measure, set of measure 1. And that was the first claim. Let's look at a statement of the question again. First claim was Cantor sets mapped onto a measurable set of positive measure. Yeah, I don't know exactly what set it was, but we just established that under psi, it's mapped to a set of measure 1, and 1 is positive. Second claim maps a measurable set, a subset of the Cantor set, onto a non-measurable set. Okay, that's a little surprising, I think, because psi is not a bad function. It's a strictly increasing continuous function with certain mapping properties. Yet it's mapping a measurable set to a non-measurable set. And I can ask the open-ended question, what's a non-measurable set look like? And you got no idea because you use the axiom of choice to go through and create it. So I don't know what these non-measurable sets look like. I'm a bit surprised we can get a non-measurable set. I have no clue what that looks like as a image under a strictly increasing continuous function. Just the continuous part would surprise me, but it's got even added constraints. So we can get a non-measurable set as an image of a measurable set, a subset of the Cantor set. You know what the Cantor set looks like? I can describe it. It's closed. That doesn't mean subsets of it are closed, but it's a closed set of measure 0. So this comes across as a bit surprising. All right. As stated in the 4th edition of the book from section 2.7, I think it is, Vitali's construction of a non-measurable set. We're in 2.7, section 2.6 in the 4th edition. Implies that if you have a set of positive measure, it contains a non-measurable subset. I often go through the notes on non-measurable sets from the 3rd edition of the book, and in there it's also claimed that every set of positive measure has a non-measurable subset. I think maybe it's an exercise in the 3rd edition of the book. But no matter how you slice it, psi of C is a set of positive measure. It was measure 1, as we saw in the last slide. So it contains some non-measurable subset. Let's call it W. Well, the set psi inverse of W is measurable by proposition 2.4. Psi inverse of W is a subset of the Cantor set, right? Psi of C contains a subset W. The inverse image of W is a subset of the Cantor set. The Cantor set has measure 0. Cantor set has measure 0. Monotonicity tells you this thing here, psi inverse of W, subset of the Cantor set, also has measure 0, and so is measurable. So psi inverse of W is a measurable subset of C, and under psi, it's mapped to this non-measurable set, W. Second part, surprising, not very constructive, because I don't know where this non-measurable set of psi of W came from. Sorry, psi of the Cantor set. I don't know where non-measurable set W came from. I know it exists. The theory tells us it exists. So yeah, maybe not too constructive, but you can map under strictly increasing continuous functions measurable sets to non-measurable sets. That's potentially a big problem when we start trying to do Lebesgue integration. All right, let's use that previous result to show the following. There is a measurable set, a subset of the Cantor set, that is not a Borel set. We couldn't even describe what all the Borel sets look like. I've made the claim somewhere along the lines, I dare any of us to come up with an example of a set that's not a Borel set. Well, the non-measurable sets are not Borel because the Borel sets were measurable. How many non-measurable sets do you know? Well, really, we just got that one we created. I could play with it and get more from it. In fact, we will in the supplement. But really, I only have one technique of constructing non-measurable sets. So finding sets that are not measurable was really elusive. Finding sets that aren't Borel, totally different question, but still pretty tough stuff to do. We're going to do it as follows. So the claim is there's a measurable set, subset of the Cantor set, that's not Borel. So when I say Borel sets, we're not talking about all measurable sets. And we haven't really tied that down until now. Okay, so take the strictly increasing continuous function psi that we had in the previous proposition. It mapped a measurable set, let's call it A. Actually, it was the inverse image of W in the notation we had there, onto a non-measurable set B. Actually, B was that set W we had in the previous proposition. So here's you a function that maps measurable set A onto measurable set B. Need an exercise from chapter 2, exercise 2.47 says a continuous strictly increasing function, which psi is, that's defined on an interval, need all those hypotheses, which psi is, maps Borel sets to Borel sets. Well, then A can't be a Borel set. If A were Borel, then its image under psi, that is set B, would be Borel. Set B is not Borel. Set B is not measurable. Non-measurable sets ain't Borel sets. So A can't be a Borel set either. Yet A is measurable. That comes in from proposition 2.21. So we've got this measurable set, a subset of the Cantor set, that is not measurable. The not measurability going through an argument about how Borel sets are mapped under continuous, strictly increasing functions defined on intervals. So a lot of the weight goes on that exercise right there. But in appropriate hypotheses, Borel sets are mapped to Borel sets by sufficiently constrained functions. You know what a Borel set looks like? Yeah, sort of. I got to appeal probably to sigma algebra properties, given what the Borel sets are. So, some bad news, the Borel sets, they don't include all the measurable sets. That's the real punchline of this question. The sigma algebra Borel sets does not include all the measurable sets. I like to tell you what sets look like. And I can't even tell you what all the Borel sets look like. And that doesn't even include all the measurable sets. Ugh. I can tell you what an open and closed set looks like. I can tell you what an F sigma and a G delta set looks like. I can tell you what an F sigma delta set looks like, though the explanation becomes pretty clunky and so forth. But if you'll recall, that chain was alleged not even to include all the Borel sets. Not every Borel set is either a G delta sigma, delta sigma, delta sigma, blah, 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 or an F delta sigma, delta sigma, delta sigma. Did I get it right? Those chains of functions, those chains of sets I can describe in terms of unions and intersections and so forth. But that didn't even include all the Borel sets. The sigma algebra stuff, in a sense, it allows you to mix together G delta sigmas with F sigma deltas. That we never did in that description of those chains of sets. But, geez, I was having trouble describing Borel sets, and the Borel sets don't even include all the measurable sets, as we now see by an example, elusive example, right? We were guaranteed the existence of this non-measurable subset. All of this falls on the axiom of choice's shoulders, ultimately. But what we'll do in the supplement to this section, as I mentioned earlier, we'll show that the cardinality of the sigma algebra of Lebesgue measurable sets is the same as the cardinality of the power set of the reals. In fact, it's the same as M sub 0, the collection of sets which have measure 0. And that's what we'll show in the supplement. It's been claimed that the Borel sets are a collection of sets only of cardinality aleph 1. This I'm not prepared to prove, but I got a reference for you. If you'll buy that, then I can put together a simple cardinality argument. Yeah, if the measurable sets have cardinality aleph 2 and the Borel sets have cardinality aleph 1, a whole level of infinity lower, there's a bunch of measurable sets that aren't Borel sets. But more of that in the supplement, and we'll address that with cardinality arguments. This was addressed, if you'll notice, really with, I want to say, no cardinality arguments at all. Well, we did do something about showing the Cantor set was uncountable, and we had our reasons for that. So there's section 2.7. Let's do the supplement next. It's a lot more brief and a lot less detailed and a tiny bit less rigorous to boot. It's some stuff that's not in the book, but it relates to cardinalities and answers, I think, some natural questions. Have a nice day. I'll catch you later.